So this is my presentation on our second lab, which was on projectile motion. The purpose of this lab was to measure and model projectile motion, compare experimental data to physics-based computational models on GlowScript, and analyze how air-resistant affects motion. So first we had a model of our X position and Y positions that we found on Tracker after analyzing our thrown paper ball. And then our computational models, we had one of motion with force of gravity and one with motion with the gravity and a drag component included. So fundamental principles, we have Newton's second law, which states force equals mass times acceleration. In this case, acceleration is gravity, and that's 9.8 meters per second squared. And then in this case, we have a drag component because of air resistance, and gravity plus drag is F net equals mass times gravity minus b times velocity squared v hat, which that second part is the drag component. And then preview result, the gravity only model predicted a longer and smoother path that was observed, while the gravity plus drag model provided a closer match to the experimental data. This confirmed that air resistance plays a role in the motion of our object. The main physics idea is the position graph will be curved because the y component has acceleration due to the force of gravity, and the x component's velocity is constant in an ideal motion, but our paper ball experienced some air resistance. And then the model, we computationally modeled a perfect projectile motion using the same initial conditions with and without an air resistance factor to compare to our model of observed X and Y positions over time that we found from Tracker. And then our system was paper to ball, our surroundings was air and Earth's gravitational field. Then the initial conditions, our mass was 0.145 grams. And then you can see my X initial position, Y initial position, the initial time, which is 0 seconds, and our velocity initial, which we found from taking the slope of the first 2 points. And then here is my experiment. As you can see, we threw a paper ball. I had a meter stick in there to calibrate Tracker so it knew how to correctly take the measurements. And then I tracked the ball every frame of the video. And then I put it into Excel, and you can see my graph of the Tracker positions. And then on the top left corner, you can see the Tracker graph. Then the computational model, same system and surroundings, and then same initial conditions, except now the drag we used as 0.01 for our model that included drag, and for our model that didn't include drag, we set this b value as 0. And here in this code, you can see where I update the F drag, where I update the force of gravity, and then where I update F net. And then I update the ball, the velocity of the ball, and then the position of the ball, and this loops through until the end of the timestamp, which is at 0.67 seconds. And then here are the graphs that I got from the the GlowScript data. So this is without drag and with drag. As you can see, there's not too much of a difference, and this could be because, well, actually, I'll talk about my possible errors in just a second, but here's a side-by-side of the Tracker graphs and the GlowScript graphs. So you can see the one with drag is maybe slightly better, but there's not too much of a good correlation. And it starts at different positions because the computational models had a strong gravity affected it stronger than in my Tracker model. So all of the graphs have the curvature expected, since we expected the ball to begin moving upwards at a decelerating rate and reach a max and then fall at an accelerating rate due to the force of gravity. However, the computational models with and without drag after reaching the peak fall much faster than our ball did in the experiment. Possible error: the air resistance or drag that we used could not be properly calculated because a crumpled up piece of paper has so many ridges, the calculation would be nearly impossible. So we had to guess a drag value, and the drag value may have not been close to what the actual amount of air resistance affecting our ball. And this would explain why the paper ball was less affected by the acceleration due to gravity, because air resistance was acting against gravity. And then questions terminal velocity. In the gravity-only model, velocity keeps increasing, so there's no terminal velocity, but with drag, the forces will balance at some point, giving a terminal velocity, but our experiment was too short to see it because we would have to have a velocity that equaled the square root of v divided by mg, and we didn't have enough time for the ball to reach the speed. And then if the ball was thrown straight up without drag, it would be a symmetric flight, so the same time, and with drag, it would be a longer descent because the drag slows falling, so the total time increases. In conclusion, we showed how projectile motion is modeled. The drag slightly improved agreement with our experimental data, and our computational modeling allowed us to test conditions beyond what is easy to measure in the lab.